Imagine someone you love suddenly collapses. Their heart stops, and no one knows when or if they'll come back. That's cardiac arrest. It's swift, it's silent, and it's often fatal. What if we could change that? What if we could recognize the early warning signs and intervene in time to save lives? When my team and I joined this lab, it wasn't because of cardiac arrest specifically, but it was rather because we wanted to be part of something bigger, a lab that could help us grow in understanding the impact of neurocritical care. We were assigned to the vagotomy project, and where we focused on cutting the vagus nerve and how that impacts brain activity, blood pressure, and neurological recovery during an asphyxial cardiac arrest model. At first, we didn't know how to connect the dots of our project. We understood that the vagus nerve played an important role in brain-to-heart connections, but regardless, the project was so new to us, and then the ongoing research produced non-significant results that were a bit difficult to interpret. But then we came across a previous study in our lab, one that linked early spreading depolarization onsets detected during cardiac arrest was linked to better neurological outcome. And as we dug deeper with the help of our lab mentors onto what exactly that entailed, we realized we needed to understand more than just spreading depolarization onset. We needed to look at its duration, its offset, and also the role of Mayer waves, which are brain-heart oscillations that could give us clues about underlying arrhythmias that actually contribute to negative outcome. And these weren't just concepts from a textbook, these could be real-life indicators of a threatening event. As a result, we decided to focus on how these brain-heart connections could give us early warning signs. If we could track these dynamics, we might be able to predict when a person is heading towards cardiac arrest and intervene before it's too late. And this isn't just about gathering data, it was about finding something that could save a life. I remember when my old boss told me when I was leaving work to work on cardiac arrest research, he said, "They're dying anyway. What's the point?" Back then, I didn't have a good answer as to why cardiac arrest research was important, but now I definitely do. So, dying isn't always the end. The heart may stop, but the body is still sending signals. And even if we can read those signals, we might be able to intervene. And perhaps we can say this is the heart of our project. Though significant spreading depolarization and Mayer waves results from multimodal monitoring, we found that these two phenomena could serve as ultra-early markers for prognosticating the outcome of cardiac arrest, and then tracking these signals could offer crucial insights into the timeline of it, helping predict where we might intervene and how we might intervene. In emergency or ICU situations where vitals fluctuate rapidly, having reliable indicators like these could drastically change how we respond to and save lives. Overall, what started as a project we weren't sure about turned into something we genuinely cared about. As we navigated through this research, my team and I also grew in understanding each other and the value this research brings to each of us. For the outside world, it's just a student research project, but for us, it's part of a larger conversation, one that contributes to future change. While research is still in its early stages, we believe it's a step toward giving doctors a tool to save lives and change the outcome of cardiac arrest. Thank you.